Early 1945, the Pacific Ocean lay quiet after a night of storm and gunfire. Waves rolled against a coral reef near the Philippines, carrying with them the remains of a once formidable aircraft. Its silver skin, torn and scorched, bore the faint letters U.S. Navy and SBD Dauntless, the same dive bomber that had ended Japan's proudest carriers at Midway. At dawn, a small Japanese patrol craft approached. Sailors in faded uniforms leaned over the rails, ropes in hand, pulling the battered machine from the surf. Its cockpit glass was shattered, its wings folded awkwardly against the tide, but the frame was intact. Hours later, it would be hauled onto the dock at Yokosuka Naval Air Technical Arsenal. There, under the gaze of Japan's top aviation engineers, the Dauntless would reveal secrets they had never imagined, a machine so ordinary in appearance, yet built with a logic their factories could no longer reach. In the early years of the Pacific War, the Douglas SBD Dauntless was easy to underestimate. It was slow, angular, and looked more like a relic of the 1930s than the cutting-edge machines that now filled the skies. Yet when the U.S. Navy needed precision over spectacle, the Dauntless became its silent weapon. From the Battle of the Coral Sea in May 1942 to the turning point at Midway a month later, the SBD proved that accuracy and resilience could change the course of a war. The Dauntless was born from a doctrine that favored precision over speed. Its perforated dive brakes allowed pilots to plunge almost vertically at 250 knots, release a single 1,000-pound bomb within meters of its target, and pull out just above the wave tops. It was a brutal test of nerves and engineering alike, one that Japan's fleet soon learned to fear. During those few fateful minutes on June 4, 1942, Dauntless crews struck the heart of the Imperial Japanese Navy, sending Akagi, Kaga, Soryu, and Hiryu to the ocean. The loss of 4 fleet carriers crippled Japan's offensive power forever. But the aircraft's real secret wasn't its bomb or its dive, it was the unseen strength inside, the riveted spars, the rugged engine mounts, the redundancy of its controls. To America's engineers, these were standard practices. To Japan's, they were luxuries, the product of factories untouched by bombs, supplied by endless steel, and staffed by trained workers. By 1944, Japan's Navy wanted to know how such a simple aircraft could withstand so much punishment and still return to its carrier. And so, when an intact SBD washed ashore, their engineers saw not wreckage but revelation. By 1944, Japan's once dominant navy was in retreat. The carrier groups that had swept across the Pacific in 1941 were now scattered and bleeding. Pilots were scarce, fuel was rationed, aluminum was recycled from wrecks. Factories that once produced sleek Zeros now worked under blackout conditions, bombed by night, starved of material by day. And yet, within the walls of Japan's technical institutes, a quiet determination remained to understand why America's machines kept winning. At the Yokosuka Naval Air Technical Arsenal south of Tokyo, teams of engineers and metallurgists examined every captured piece of Allied technology they could recover. Guns from downed P-38s, instruments from B-29 wrecks, fragments of Corsair and Hellcat wings. But none of those were intact. Each was a mangled puzzle, destroyed before its secrets could be read. That changed when word arrived from the Philippines. A relatively undamaged SBD Dauntless had been salvaged from shallow waters. It was the same type of aircraft that had shattered Japan's naval supremacy at Midway, the same model that Marines flew relentlessly over Guadalcanal and Bougainville. Now one sat before them, wings folded, riddled with corrosion, but whole. The Dauntless was transported under guard to Yokosuka in late February 1945. There it was placed in the hangar reserved for high-value enemy technology. Senior engineers from Mitsubishi and Nakajima were summoned to assist, eager yet uneasy. They knew this aircraft represented more than a mechanical curiosity. It was a glimpse into the mind of an industrial adversary whose factories had turned precision into mass production, an art Japan's struggling industry could no longer imitate. As the inspection began, what they discovered in the Dauntless's battered frame would shake their understanding of engineering itself. The engineers began with what they could see, the skin of the aircraft. Under the harsh light of the Yokosuka hangar, the Dauntless's fuselage looked ordinary, riveted aluminum panels, fading navy blue paint, traces of salt and sand. But as they peeled back each layer, a different story emerged. The rivets were perfectly spaced, each panel fit with millimetric precision. Even areas never meant to be seen by pilots or crews, the undersides of bulkheads, the hidden flanges behind armor plating, were finished to identical tolerances. When they dismantled the wings, the shock deepened. The structure revealed an elegant balance between strength and simplicity. The main spar, a single forged beam of high-grade aluminum, was both light and unyielding. Its design allowed the Dauntless to withstand the extreme stresses of 70-degree dives without twisting or shearing, something Japanese dive bombers like the HID-3A Val often struggled to endure. Then came the dive brakes, the Dauntless's signature feature. To Japanese engineers, the perforated flaps looked primitive at first glance, thin metal plates peppered with holes hinged along the trailing edge. But wind tunnel tests at Yokosuka soon revealed their genius. At high speeds, those perforations disrupted airflow turbulence, keeping the plane stable during its near-vertical descent. Where the Val needed precision timing and a skilled hand to avoid structural failure, the Dauntless relied on predictable physics and smart design. Every system inside reflected the same philosophy, simplicity that performed under pressure. The hydraulic lines were color-coded and insulated. The fuel tanks were self-sealing, using layered rubber compounds that swelled when punctured, a technology Japan had not mastered. Even the instrument dials, etched in luminous paint, were ruggedized against vibration. To the Japanese engineers, this was not just a machine, it was a statement of industrial philosophy. It spoke of an enemy that trusted process over improvisation, assembly lines over artisanship, endurance over elegance. They had been fighting pilots, now they were confronting engineers, and realizing who had truly built victory into their wings. The deeper the inspection went, the more humbling it became. Inside the Dauntless's cockpit, Japanese technicians found an instrument layout that reflected not just precision, but empathy for the pilot. Every dial, switch, and lever followed an intuitive pattern built for clarity in chaos. The gun sight alignment was exact. The radio controls were sealed against moisture. Even the oxygen regulator and canopy release lever had redundant linkages. To men who had flown cramped, fragile cockpits built in haste, this attention to human design was almost foreign. They compared the Dauntless to their own D-3A Val, the dive bomber that had once terrorized Pearl Harbor. Where the Val relied on pilot finesse, the Dauntless trusted its structure. Its crews didn't need heroics, the plane absorbed the punishment itself. Armor plate beneath the pilot's seat, bullet-resistant glass ahead of him, and a reinforced firewall behind the engine all added weight, but also survivability. In Japanese doctrine, such excess was weakness. In American engineering, it was foresight. Even the rear gunner's station, often overlooked by Japanese designers, showed remarkable thought. Twin .30 caliber Brownings were mounted on a flexible ring that could traverse 360 degrees, with hydraulic assist for quick aiming. Spent casings were ejected cleanly into a vented tray, keeping the workspace clear. The compartment was cramped, but everything was within reach, a harmony of man and mechanism. To the engineers at Yokosuka, this aircraft embodied a contradiction, a dive bomber that was both industrial and personal. Every element told the same story, precision born not from genius but from consistency. Where Japan's aviation factories were forced to hand-fit every rivet, American plants built thousands of identical parts that required none. Each Dauntless carried the signature not of a craftsman, but of a system Japan could admire but not replicate under fire. That realization, that victory came from process, not merely skill, struck deeper than any bomb that the Dauntless had ever dropped. The disassembly reached its peak in early March 1945. On the hangar floor at Yokosuka, the Dauntless lay stripped to its skeleton, a gleaming framework of rivets, spars, and wiring. Technicians gathered around its heart, the Wright R-1820 Cyclone engine. An 1,200 horsepower, 9-cylinder radial masterpiece that had powered not just bombers, but the very momentum of American industry. Each cylinder head was identical down to the thousandth of an inch. The pistons, connecting rods, and crankcase surfaces bore no imperfections visible to the naked eye. To Japanese machinists working with war-worn lathes and dwindling alloy stock, this was an unsettling sight. When the engine was cut open, the revelation deepened. Even after months in salt water, its internal components showed minimal corrosion, a testament to superior alloys and coatings. The lubrication system was redundant, with double filtration and pressure regulation that ensured consistent performance at every altitude. The magnetos and wiring harnesses were precision-fitted, built to survive vibration, heat, and shock. The Japanese engine specialists noted this in their reports: no wasted material, no excessive complexity. Part serves exact purpose. They began comparing it to their own engines, the Mitsubishi Kinsei and Nakajima Saki. Both were marvels of design ingenuity, but fragile in practice. Oil leakage, cracking under dive stress, and uneven manufacturing were common. The Dauntless's Cyclone, by contrast, represented something different, not brilliance, but repeatability. It was the manifestation of a production line that could guarantee excellence, even when built by thousands of anonymous hands. As the engineers measured tolerances, one of them reportedly murmured what others were already thinking: even if we knew how to build it, we could not build enough. That quiet admission marked the turning point, the moment Japan's top minds began to understand that the war was not only being lost in the skies, but also in the factories. The next stage of testing moved from the hangar floor to the airfield. By mid-March 1945, Japanese engineers had restored the Dauntless's control surfaces and connected the hydraulic systems for limited ground trials. The aircraft could not fly again, but it could breathe. Its control linkages moved smoothly. The dive brake system extended and retracted with perfect synchronization. When they powered the cockpit instruments using an auxiliary generator, every gauge flickered to life as if built yesterday. Altimeter, compass, oil pressure, fuel mixture, all steady, all calibrated. It was as though the aircraft itself refused to age. Then came the comparison tests. Side by side stood the HID-3A Val and the captured SBD Dauntless. The difference was unmistakable. The Val was graceful but delicate, its wings easily warped under repeated dives, its rivets prone to fatigue. The Dauntless, heavier and blunt-nosed, was built like a warship in miniature. It could dive steeper, hit harder, and return to the carrier again and again. Technical officers recorded every measurement: the SBD's wing loading, the strength of its landing gear, the armor distribution around its cockpit. What struck them most was how every component was built for longevity. Even the bolts securing the bomb cradle were treated with anti-seize compound, a detail so mundane, yet so foreign to Japanese wartime practice. The final report, handwritten and later found by American occupation forces, contained a single line that summarized months of study. We cannot match this manufacturing discipline, not with our materials, not with our time. For the men at Yokosuka, it was an admission of defeat spoken in the language of metallurgy and rivets. The Dauntless had already destroyed Japan's carriers in battle. Now, even in captivity, it dismantled the illusion of technological parity. Its greatest weapon was not the bomb beneath its belly, it was the precision built into every seam of its frame. The examination concluded in April 1945, as Japan's cities began to burn under relentless B-29 raids. At Yokosuka, the final technical report on the SBD Dauntless was quietly archived under Naval intelligence files marked confidential, Foreign Aircraft Study No. 92. It included meticulous sketches of the wing spars, hydraulic schematics, and alloy analyses of the Wright Cyclone engine. The tone was professional, but the subtext was unmistakable, admiration tinged with despair. Engineers noted that the Dauntless embodied something Japan could not replicate: a system of manufacturing excellence. Its materials were consistent. Its design philosophy was unpretentious. Every part had been engineered to work in harmony with hundreds of others built thousands of miles away, by different hands in different factories, and yet all fit perfectly. In their closing remarks, the Japanese metallurgists wrote, "This structure represents an organization more powerful than a weapon." Outside the hangar, reality had already confirmed their words. The same factories that built the Dauntless were now producing B-29s, landing craft, and Liberty ships in staggering numbers. The aircraft they had studied was not an exception. It was a symbol of an entire nation's industrial rhythm. When American occupation forces arrived at Yokosuka in September 1945, they found the remnants of that captured SBD Dauntless still in the corner of the hangar, stripped, rusted, but carefully preserved. Stacks of engineering notes surrounded it, written in both Japanese and English annotations. The U.S. intelligence officers who reviewed them recognized the respect in the handwriting, measurements lined with care, comments underscored with precision. The Japanese had not mocked their enemy's creation, they had studied it like a textbook. For Japan's engineers, that aircraft became both an ending and a beginning. In the ruins of their defeated empire, they finally grasped what America had built: not just an airplane, but an ecosystem of excellence. Within a decade, many of those same minds who once studied the Dauntless would help rebuild Japan's post-war industry. They carried forward the same lessons, that precision, consistency, and discipline matter more than speed or daring. The SBD Dauntless was scrapped soon after, melted down like countless relics of war. But in its brief captivity, it had achieved something extraordinary. It turned its captors into students, and its wreck into a lesson that would echo far beyond 1945. In the silence that followed Japan's surrender, the engineers who had examined the Dauntless walked through the ruins of their workshops with notebooks still in hand. What they had seen in that captured American dive bomber lingered in their minds long after the war ended, not its power nor its victories, but its clarity of purpose. The SBD Dauntless had not been built by genius alone. It was the product of patience, precision, and a nation's faith in its own machinery. Every rivet, every joint, every instrument spoke of an industrial rhythm that never faltered, even in war. To those who studied it, the lesson was unmistakable. Strength is not born from speed or pride, but from systems that never compromise on quality. In time, that understanding would guide Japan's rebirth. The same engineers who once measured America's machines now built their own, better than ever. The Dauntless had ended empires, but it had also planted the seeds of renewal, a reminder that even in defeat, knowledge endures.